Y'all ready for math? We're back, folks. Pre-calculus honors. Okay, little 2-week layoff right there. Hope you did well in your advanced placement exams. I hope you're able to actually submit answers. I know there were some issues with that. Okay, that's because the College Board is actually run by squirrels, something we'll speak about next year. I don't know if I mentioned that to you this year yet, but we got more work to do in this class, okay? This is an honors math class right here. We still got more material to get through. I know some people are like, oh, APs are done, so the school year is over. No, it's not the way it works, okay? Seniors, I get it. Your senior year here, APs are over with and you want to be done right now, but you still got work to do. You decide to take an honors math class. We got to get through the material that I normally get through. And juniors, don't even start with me, okay, with this whole, AP exams are senioritis. You can't have senioritis, okay? You're a junior, and there is no junioritis. We have work to do. Okay, so, what were we talking about? Get a little star action going. Star! Last chapter was actually chapter 4, so we're going to go chapter 4 continued, because there's a little bit more going on here. ... And chapter 4 dealt with integration, okay? The antiderivative, essentially the opposite of differentiating would be integrating. And we spoke about a specific type of integral. If you want to recall, we talked about the indefinite integral, the indefinite integral. Okay, and the indefinite integral is when you integrate some function, we'll call it f of x. You always need to indicate the variable that you're integrating with respect to, okay? You got to put that little dx right there. We'll talk a teeny bit more about that today. And remember, when you integrate, that's somebody's derivative in there. Whose derivative? The answer's derivative, okay? And look, there's no notation for a function if their derivative is f of x. So usually we say big F of x. Don't forget to add c right there, very important. But this right here is not implied mathematical notation. You have to actually say if you take the derivative of the answer, you get the integrand back. Remember that guy right there is going to be the integrand. So we say where big F prime of x is equal to little f of x, okay? And all that is a disclaimer that tells you integrated correctly. If you just left it written this way, it would say, hey, if you integrate a function, you just get some other function back. But it has to be a function such that when you take the derivative of that function, you get the integral back. You can avoid that situation if you do the integral of f prime of x with respect to x. It's actually integrating a rate of change. We'll speak about that a teeny bit in this topic, but only to clarify why we do something that we're going to talk about today. That's something we really don't get until next year. But remember, that's somebody's derivative in there. Whose derivative? F of x's derivative. Don't forget to add some cookies. And then we're good to go. So this is probably a better way to actually write it out, but it's also important to talk about this as well, because you don't always identify a function, an integrand, as a derivative, even though technically every function could be some other function's derivative, okay? But it's something we'll speak about. We need to speak about it. Today, we're not talking about the indefinite integral. We're actually going to take out that in and speak about the definite integral, which, believe it or not, graphically has to do with area. So chapter 4 continued right here, area and the definite integral. Area and the definite integral. Okay, and let's speak about the definite integral. Before we do that, though, let's do a little example, okay? Hopefully you printed out these notes or you just wrote this problem down, you're staring at it on the computer screen. Given f of x is equal to x, they want to know what's the area between f of x and the x-axis from x equals 1 to x equals 3. You might be like, what the heck is this here? Area, area between f of x and the x-axis from x equals 1 to x equals 3. What the heck is going on here? I don't know, maybe you want to draw like a little diagram, no calculator here. People are like, well, without a calculator, how am I supposed to graph f of x equals x? Well, even Mickey Mouse should know how to do that, okay? This is just the line, y equals x right here. All right, so easily we can graph y equals x. Does not need to be perfect. Do the best you can. Looks like my slope is a little bit too steep, but whatever, close enough for government work. All right, so y is equal to x over here, and we want the area between f of x and the x-axis. And if I just asked you that, what's the area between f of x and the x-axis? Well, that would be infinite, right? Here you can see f of x. Here's the x-axis. This thing keeps going. So you're talking about an infinite amount of area, and you're not even considering the area in the left direction, between the function and the x-axis. Here, the region's above the x-axis. Here, it would be below. That changes things around a little bit. We'll speak about that when we need to. But for now, they got to give you some kind of bounds, some kind of limits, and here they're specifically saying from x equals 1 to x equals 3. So maybe x equals 1 is right here. Here's x equals 2. Here's x equals 3 right here. We even got corresponding points, right? This is the point 1, 1. And this right here would be the point 3, 3. And you want the area between f of x and the x-axis. So we're actually talking about this region right here. Okay, so really we're talking about this shape. I don't know why I would close that pen when I still need to use it. Whatever. All right, we're talking about this shape right here, which, believe it or not, is actually a trapezoid. It's a right trapezoid. You're supposed to know how to do the area of a trapezoid. It's actually part of the advanced placement curriculum. We'll talk about that next year or a little bit later this year when we speak about something known as the trapezoidal rule. Most people, even if they're good with the area of the trapezoid, they'll break this up and they'll be like, okay, you know, this could be like an SAT question, right? They ask you this right here, no calculator. We've now broken this up into a rectangle and a right triangle. We know the rectangle has base 2, height 1, so we know that his area is going to be 2 right there. This right triangle, remember the area of a triangle, always 1/2 base times height. And for a right triangle, you could always say that the legs represent the base and the height because they form a right angle, okay? So to get the area of a right triangle, you could really just do 1/2 leg times leg. So this distance is actually 2. This distance is 2. 1/2 times 2 times 2 is going to be 2. And thus that we get the area is equal to 2 plus 2, which last I heard is equal to 4. Some people say 2 plus 2 is equal to fish, okay? But you have to Google that to see that solution. If I had a smartboard, I'll show you, but it's kind of silly doing it this way. Anyway, so that shouldn't be too terrible right there. People are like, oh, wow, that's calculus. Like, what the heck is going on? Well, believe it or not, you could do the same problem by calculus over here, by calculus. You know, why wouldn't you want to do it by calculus, okay? And we're going to start talking about today that if you want the area between a function and the x-axis, you integrate that function, okay? Which seems kind of weird. We're going to take the integral. We want the area between x and the x-axis, right? Y equals x, f of x equals x. So we're going to integrate x, and then we're going to make sure we integrate it with respect to x. You have to indicate the variable you're integrating with respect to. You know, and if you look at this right here, and by the way, the calculus police, if I tell you, hey, every time you want the area between a function and the x-axis, just integrate that function, the calculus police, if they were listening, are they listening? They would come in here right now and, you know, handcuff me and throw me in prison. You know, because that's not exactly true. You know, some people think the area, the integral is the area under the curve. That's a very, lay definition, okay? There's really a lot more that's going on. Integrals can be negative, okay? Areas can't be negative. So the integral, the indefinite integral does have something to do with area, but it's not always exactly the same as area. At first it will be, okay, for the first bunch of problems we do, but we'll speak about situations when it's not. We'll get more into those situations next year. You know, the problem with this is if you want the area between a function and the x-axis, integrate that function, well, you need to consider those limits, okay? Otherwise, this answer would be infinite right here, okay? And this is an indefinite integral, okay? It would actually give you a function back. We know how to integrate this, x squared over 2 plus c. You know, and you should be able to do that. Go back and look at those videos if you need to, do some review. If you can't integrate like we learned last chapter, you're not going to be able to do anything in this chapter. But here's how you actually set up those limits, okay? On the integral sign, we want to go from x equals 1 to x equals 3. So we're going to start at x equals 1. So down here, we're going to write a little x equals 1. And then we're going to end at x equals 3. Up here, we're going to put a little x equals 3, okay? And this thing right here, this x equals 1, this is known as the lower bound. Some people actually call it the lower limit. I don't like to use the word limit because then it's confusing with, you know, what we spoke about in chapter 1, limits and continuity, but it's still the same thing technically. So this is the lower bound, which is the limit, and this guy right here is going to be the upper bound, or the upper limit, if y'all want to say it that way, okay? So this is actually the way to set it up, and it's kind of silly. There's like a lot of busy stuff going on right here. Really, you could just write this. You could say the integral, and then we're going to say from 1 to 3 of x with respect to x. It's not necessary to write the x equals 1 and the x equals 3. It's implied those are x bounds, okay? How do I know those are x bounds? Because I'm integrating with respect to x. So if this was a dt right here, these would represent t values, okay? So that's important. You know, whatever your bounds are, they have to correspond to that independent variable, the variable you're integrating with respect to. So if you want the area between x and the x-axis, from x equals 1 to x equals 3, want the area between a function and the x-axis, integrate that function. And then the lower bound, usually if you're setting up the integral on your own, it's the lower number and the upper bound is the higher number, but it doesn't need to be that way, okay? You could actually take this thing and you could integrate starting at 3 and ending at 1. You're actually integrating backwards. A lot of crazy things you can do with integrals. We're just going to take it slow for now. By the way, if you want to know what this is in words, we're going to say the integral from 1 to 3, the integral, comma, from 1 to 3 of x with respect to x. With respect to x. Okay, you could say the integral of x with respect to x from x equals 1 to x equals 3. Bunch of different things. You don't need to say it's x equals 1 and x equals 3. It's implied because it's with respect to x. Okay, but regardless, this is the integral you'd want to set up right here. So hopefully not too terrible. How do you evaluate a definite integral? Because that's what this is. This is a definite integral because it's not infinite. Okay, I've actually defined bounds here when I want the area between the function and the x-axis. Well, here's how we do it. Okay, the first thing we do is we actually integrate. Ain't it great? I think it is. Okay, so if you integrate x to the first power, add 1 to the exponent, divide by that number, we get x squared over 2. Add some cookies here. And that would be the answer if it was an indefinite integral. But now that it's a definite integral, we're going to take this formula we have right here, and we're going to evaluate it. Remember how we did like, dy over dx? Evaluated at x equals 1, just another way to write up the notation. So that's the little evaluation line right there. You need parentheses around this because it's a binomial. I want to evaluate the entire thing from one x value to another x value. I'm going to say from x equals 1 to x equals 3, okay? Always put that lower bound on the bottom, upper bound on the top, okay? And you could really just write that up this way. You could say, let's take x squared over 2 plus c, and evaluate it from 1 to 3. You don't need to put the x equals there. It's implied it's x bounds because of the x inside here. That's what the variable actually is. What's our next step? Well, our next step is that we actually plug in the bounds and we subtract, okay? Because what's really happening when you do a definite integral is you're getting a change, okay? You're actually getting a change in a function. What does a function always represent? Very good. Y values, okay? So really getting the change between two Y values. And to get the change between two things, you just subtract those two things, okay? The thing is, if you want the change from one Y value to another Y value, you need to take the later Y value and subtract from it the sooner Y value, okay? And that might, right now you're like, what the heck are you talking about? Well, really, you need to take the Y value at x equals 3 and subtract from it the y value at x equals 1. If you want the change between two y values, you always want to take that y value that's further to the right and subtract from it the y value that's to the left. That might not make any sense to you, and that's fine, okay? And what's really happening is that technically this is a function's derivative here. You're integrating a rate of change, which means you're getting back the original function, and then you're going to subtract y values to get the change in y values. We'll talk about that, okay? For now, you can just memorize this. Always plug in the upper bound first. So it's always the upper first. Plug in first. Plug in first. And plug it in for what? Well, it says, that's his first right there. Well, it says x equals, right? Okay, well, it did. So x is equal to 3, so plug into 3. So 3 squared over 2 plus c minus, now we plug in the lower bound. Okay, we're going to plug in second. Plug in second. Back in. All right, so we subtract the plugging into the lower bound, parentheses again, so 1 squared over 2 plus c. And that's how you evaluate the definite integral. You can see you get back what? 9 halves plus c. Distribute this negative. This is a 1/2 right here, so minus 1/2. Here's the interesting thing. I know a lot of people like, oh, a -1 times a c, a negative times a constant, just another constant. That's true, but you got to understand that these two c's came from this c right here. They're the exact same thing. So when you subtract them, they will cancel out, okay? So we'll put a negative c here. And from now on, when you do a definite integral, when there are bounds on the integral sign, you do not need to put the plus c, because the plus c is going to cancel out every single time. And here you can see we have 9 halves minus 1/2, which is equal to 8 halves, which is just equal to 4. Whoa, whoa, what's that feeling? You can only say what it is in French. A déjà vu. We got the same thing, okay? So you might be like, wait, what the heck was that whole integrating rate of change and later y value, sooner y value? I'll write that out in a lesson that's going to come up pretty soon. But remember, if you want the function, the area between a function and the x-axis, for now, integrate that function. Put your bounds down, okay? Lower bound, upper bound. We're going to go from left to right whenever you set up the integral yourself. Sometimes there's a 3 down there, there's a 1 up there, but we'll talk about it when we need to. To evaluate a definite integral, integrate the integrand, and make sure you evaluate it from lower bound to upper bound, which actually means that you're plugging in the upper bound first, then you're subtracting the plugging in of the lower bound. More on that later, okay? Memorize the process for now. This chapter is a little bit more about mechanics and not so much about theory, but we'll speak about it a little bit, we need to. For now, I just want you to be able to deal with the mechanics. And then some other people might be like, that's all great, Berto, but, look at this work. And look at this work over here. So the inevitable question, why? Why would we do this, okay? Why would we use calculus to get the area between a function and the x-axis? Well, good question. Because if you actually take a look at example 2, if you were now we have f of x equals x squared plus 1. We want to find the area between f of x and the x-axis. If you want the area between a function and the x-axis, integrate that function. And now it's from x equals 0 to x equals 2, okay? So we got bounds as well. But here we got a function, you tell me. And usually I'd ask people in class, we don't really have the time on a video. It's not that we don't have time. We got lots of time. I just don't have you in front of me. So really, right here, I'd normally ask, why would we need to use this method, okay? And hopefully somebody would come up with a situation where you can't calculate the area between the function and the x-axis traditionally. Before we broke it into a rectangle and a triangle, could have just used the right trapezoid if you want. But here, if you actually graph f of x equals x squared plus 1, no calculator, we all know what that looks like, okay? Y equals x squared shifted up 1 unit. So maybe like a little something like that. Doesn't need to be perfect. Here's f of x equals x squared plus 1. And now, by the way, if you just wanted the area between f of x and the x-axis, that'd be an infinite amount, okay? You're talking about all this area right here. But really, they just want it from x equals 0, which is already represented here, to x equals 2. By the way, if x equals 2, what does y equal to? 2 squared plus 1 is going to be 5 right there. So here's the region that they're actually talking about, okay? And this is not a shape that you can calculate the area of using traditional means. Some people are like, oh, that's easy, I'll make it a rectangle and a triangle. That's not a triangle, okay? That's like a curvy triangle thing, okay? We don't have a way to actually get this area. So that's why we have to use calculus here, okay? So if you want the area between a function and the x-axis, integrate that function. So let's integrate x squared plus 1. This right here, you can't just leave it like this, okay? We actually spoke about this. When you do the integral, you're actually getting the area of a rectangle. We'll speak about that in a second. This represents the height of the rectangle. And you need the base of the rectangle to multiply by the height to actually get the area. The dx, believe it or not, that's the base of the rectangle. We'll speak about that in a couple minutes, but you can see how area is coming into play. And look, right now, this would be infinite. We need to determine bounds here. You can see it's from x equals 0 to x equals 2. And if you want the area between a function and the x-axis, you can integrate that function. But believe it or not, that only works when the region's above the x-axis, which it certainly is here. You can see the region is here. And the previous problem, the region was above the x-axis as well. See, if I wanted the area of this region right here, from like 0 to -1, okay, if I wanted this area, well, if you integrate from -1 to 0, you'd actually end up with a negative answer because the region is below, okay? But these are things we'll speak about. We need to speak about them. Don't worry about it yet. The question is right now, can you set this up? Is that all right? And usually it's not too terrible for people. Let's actually calculate this here. So to evaluate a definite integral, remember, you don't need to say the x equals 0, the x equals 2. It's implied with the dx right there. First, we integrate. Hey, integrate x squared. That's x cubed over 3. Plus the integral of 1 with respect to x. Remember, that's somebody's derivative in there. Whose derivative? The answer's derivative. What do you take the derivative of with respect to x to get 1? X. And then we're going to evaluate this thing right here from 0 to 2. Remember what that means, okay? You want to plug in the upper bound first, subtract the plug into the lower bound. I didn't really explain it all that great a couple minutes ago, but like I said, we'll talk about that in a future lesson. Plug in the 2. You don't even need to actually show that you're plugging in the 2 if you don't want to. Let's do it, though, for the first time here. 2 cubed over 3. Plus, notice there's another 2 right here because there were 2 x's. That's the plugging into the upper bound. You don't really need the parentheses right there. Then subtract the plug into the lower bound, which you're going to learn to love, okay? You're going to learn to love 0 as a bound right here. Loving it. Because when we do 0 cubed over 3 plus 0, you can see that this is going to wipe out. It's just going to become 0. It makes things so much easier. So here, really get 2 cubed over 3, which is what I did on Thanksgiving, 8/3. Plus 2 over 1, okay? Let's get a common denominator here. So multiply by 3, top and bottom. So 6 over 3, minus 0 if you want to write that. Not really necessary. And here you can see that we get 14/3 as our actual answer, okay? So kind of cool right there as far as getting the answer using calculus when you can't do it by traditional means, okay? So this thing right here, this is the definite integral. I think we need a little star action going. Somebody like to give me a little star out there? What do you think, Julie? A little star? So she's looking right now. She's going, star. I'm going to say, star! This thing right here is the definite integral. The definite integral in all its glory. Technically, it's really the fundamental theorem of integral calculus, part 1, version 1, but we'll speak more about that next year. And the definite integral, a couple different ways to write it up. One way, I'm going to write the integral of f of x with respect to x but we need bounds here. So let's say the integral from a to b of f of x with respect to x. People are like, why is it from a to b? Because I don't know if a is going to be 0 and b is going to be 2. It's going to be different for every problem. And remember, when you evaluate a definite integral, which is cool, you get an answer back, right? An indefinite integral, you get a function back. A definite integral, you actually usually get a numerical answer back, okay? There are a lot of cool integrals. These eventually become improper integrals. We'll have like infinities on here and stuff. It's a BC thing. We don't do it in AB, but it's still cool to talk about. If you integrate little f of x, you get big F of x back. Don't put the plus c. It's not necessary because it's always going to cancel out. Over here, we didn't bother with the plus c because the plus c's will always cancel out with the definite integral, so you don't need that plus c. But we're going to take that big F of x, the integral of little f of x, we're going to evaluate it from x equals a to x equals b, which just means we plug in the upper bound first, big F of b, minus plugging in the lower bound, big F of a. And you still need that disclaimer, right, to say where big F prime of x equals little f of x. It's just because when you integrate little f, you're not supposed to say you get back big F. You can avoid that, and a better way to do it is to say the integral from a to b of f prime of x with respect to x, and make things a little bit more easier to understand theoretically as well. If you integrate f prime, that's somebody's derivative in there. Whose derivative? F of x's derivative. But now we evaluate it from a to b. Okay, and now we could say f of b minus f of a, and there's no need to put that disclaimer in. More importantly, this is the difference of two y values. A function always represents y values. You're just subtracting y values here. You're just getting the change in y values. Basically, if you went from y value of 2 to a y value of 5, the change would be positive 3. You do that y value of 5 minus the y value of 2, and you get 3 back. The change would be positive, but you could be a y value of 2 and then ended up at a y value of negative 3. And that means the change is actually negative 5, okay? And if you do negative 3 minus 2, you'll get negative 5. So that's why you always do the upper bound plugging in minus the plugging in the lower bound. I'll write it out a little bit more in a lesson, to come, but it's just something I wanted to actually mention right there. Before we get into the next problem, you might be thinking right now, how is the definite integral doing this? I mean, how is it able to actually calculate the exact area right there? That's a great question, and something we'll get into after this chapter most likely. We'll certainly get into it next year. It's a big part of the curriculum. But what they do before they actually get an exact area is they approximate areas, okay? And the way you want to approximate areas is to kind of, fit a couple of shapes, between the function and the x-axis that you can calculate the area of and then add all those areas up. But you don't really want to use different shapes because then it's difficult to write out an expansion if you're adding up the area of all those shapes. And what's really happening is that they started with rectangles. It's really easy to get the area of a rectangle. So if you want the area between a function and the x-axis, here's my y equals f of x. Here's the x-axis. This would be the region I'm looking for, right? The area of this whole region. One way to approximate it would be to use two rectangles, okay? And putting two rectangles in here, get the area of those rectangles, add them up. It's an approximation of the area between the function and the x-axis. It's a horrible approximation. You can see it's very much an under approximation if you get this area because there's more here that we're leaving out. We call that a lower sum, something we'll speak about next year. But what's really happening is they're just getting the area of each rectangle and adding it up. This right here, the base of the rectangle, whatever this x value is, whatever this x value is, you'd subtract them to get what the base is. Excuse me, maybe this is 2. Maybe this is 5. 5 minus 2 would be 3. That'd be that distance right there. So this distance is actually the difference of the x values. That's delta x. That's dx, that little with respect to x that we've been writing. And for each integral that we've actually had written up, okay? That little dx over here. And then believe it or not, what they're doing here is they're taking this x value and they're plugging it into the function to get this y value back. And this y value, that's actually the height of this rectangle right here. So this distance, okay, the distance from here all the way up to here, that's actually f of x, okay? And that's why the area of the rectangle is going to be f of x times dx, okay? That's the area of one arbitrary rectangle. The height is going to be a y value, and the base is just going to be a difference of x values, okay? So really, that's why you have that f of x with respect to x. That's why you can't not have that dx, okay, when you write up an integral, okay, because this actually represents the height of a rectangle, this represents the base of a rectangle. And I know, you're bored, you're like, okay, well, it's a way to get a horrible approximation. Thanks a lot, Berto. But the reason is, it's a horrible approximation, is we didn't use enough rectangles, as you start to actually use a couple more rectangles, look at that, okay? That's a nicer approximation. Still not great, okay? It's still a lower sum because it's under approximation. What's really happening here is if you look at each rectangle, they're taking the leftmost x value, they're plugging it in to get the height. You don't need to do that. There are other ways to do it. You could actually look at a rectangle right here and take the rightmost x value, plug it in to get the height. These are things we'll speak about a little bit later in the year here, and we'll talk about next year. We'll actually write out the expansions to get the area of each of these and add them up. It's kind of cool, okay, but nothing you have to worry about right now. And you can see this is an over approximation, something we actually call an upper sum. Either way, much better than that first approximation that we're looking at, okay? And you're like, well, they're still terrible. They are, I agree, okay? We need more rectangles. More rectangles. More rectangle. Whoa, look at that. You got to admit, it's getting a little bit better. I get it. Still a terrible approximation. But you have to understand, if you put in even more rectangles. Oh, now we're getting somewhere, okay? Whether you want to under approximate or you want to over approximate, the more rectangles you stuff in there, the better of an approximation you're going to get. And people are like, oh, let's stuff in like 50 rectangles, 1,200 rectangles, 3 billion rectangles. And the idea is that, look, if you want the exact area, you want an infinite number of rectangles in there. But that's ridiculous. You can't stuff an infinite number of rectangles in here. The number of rectangles can merely approach infinity, okay? And that sounds like a say it, not Sega. A limit, okay? That's a limit right there. And believe it or not, a definite integral is a limit, okay? Something that we'll speak about next year. Just like the derivative is a limit, the integral is a limit. So you won't exactly see limits, throughout the entire curriculum the way we did them in chapter 1. BC you will, okay, but AB, they kind of like take a break for a little while, then they come back later. But you're really using a limit every single time you take a derivative or an integral, okay? So believe it or not, that's what's going on there. So kind of cool, something we'll speak about next chapter, and we'll talk more about it next year. Let's do one last problem here, or how about this? Let's show this, the previous problem that we did. There's a way to do it with the calculator, which you'll need for example 3. Okay, so if I set up my little situation over here, I had y equals x squared plus 1. Okay, now into zoom 4 maybe. And, zoom 4 is not good enough, okay, because I want to see the area from 0 to 2. Zoom 4, maybe with this, no, if you plug in a 2 right here, it'll be up to 5, okay, so no good right there. So we'll take our y max. It's pretty close, though. I don't know, make it 6 just for the heck of it. And we'll look at the graph. And you can actually calculate a definite integral using the graphing calculator. Let's put a little star action over here. Star! And let's talk about, you might remember, if you hit the math button, you might remember math 8 gave you numerical derivative. We do not want numerical derivative. We want function integrate. Okay, so that'd be math 9. Math 9. 9. I like to say it that way. And when you do math 9 right here, okay. Ooh, is that the way I want to set it up? Oh, no, I want to do that. Okay, yeah, so let's speak about math 9. We'll do it with the graph in a second. So math 9, if you actually hit it, you can see it gives us our perfect integral set up. Let's do the integral from 0 to 2 of, let's actually put a 0 there. What would the answer be if it was the integral from 2 to 2? Something we actually don't really speak about this year, but you could figure it out. 0, if you want to, Mr. Pushy's IQ. Anyway, we'll do the integral from 0 to 2. I have x squared plus 1 and y1. If you want, you could just put in x squared plus 1 right here. There's nothing wrong with doing that. Or you could put in y1. And you want to integrate with respect to x, hit enter. And if you frac this bad boy up, you'll see it's 14/3, just like we got, okay? And that's very important, knowing how to use math 9 on the calculator, just like math 8, right? Calculating a derivative, you have to be good at both of those things. There'll be certain problems where I want you to use the calculator on the test, certain problems where I won't want you to use the calculator. Normally here I do a dual quest in class. First quest I hand out, you can't have a calculator, and the second quest when I hand it out, you take your calculator out. We can't do that with distance learning, obviously, so I'll just have you show work. For a problem like this, if it says show work, you better show me the entire integration process, but you could always check your answer with the calculator. That's kind of cool. You could do it by graph, believe it or not. If you go to calculate, and this is not really that useful because it gets annoying, but if you go to calculate here, and you can actually calculate the integral. right, the integral of f of x with respect to x, but you need bounds. They call it limits on the calculator. You could move left and right to get them. Like here, you could just hit enter for 0, but you could also just hit 0. If I just hit the button 0, you'll see it says x equals 0, hit enter, and now the upper limit was what? X equals 2. So I'm going to hit a 2, and watch up here. When I hit enter, watch what's going to happen on the screen. It's going to be filled up with rectangles. They were stacking rectangles right there. One, just the next one, just a little bit higher than the previous one. And there's my 4.6 repeating, my same answer for before. So that's cool because you can see the actual, rectangles being stacked over there. You can see our region over here. But really, if you want to calculate a definite integral using the graphing calculator, Math 9 is the way to go. And it's extraordinarily important. And that's what we're going to do in example 3. Example 3, given f of x equals this disgusting thing right here. Find the area between f of x and the x-axis from x equals 0 to x equals 1. Use the calculator, okay? Before it was easy to actually graph what the region would look like, but here, very difficult to be able to graph something like this by hand. You're not really expected to do it. You could use calculus to do it. It just gets extremely annoying. It's a little bit antiquated, but it could be done. All right, so 2x squared plus 1, quantity squared over here. All right, I don't know, zoom forward just to see what this looks like. Okay, in Zoom 4 with the newer calculators, they don't get you quite as close. Did I Zoom 4? I feel like I didn't Zoom 4. I hit a different Zoom, right? No, that's Zoom 4. Yeah, the newer calculators, I'm not enthralled with their Zoom 4. It's still a friendly window, but it's a little bit bigger. So if I actually take this thing and zoom in a little bit, hit enter, then it's a little bit closer. Not that it really matters, but it's nice to actually see the region. Remember, you can only use the integral to get the area between a function and the x-axis if the region lies above. And you'll notice from 0 to 1, the region does lie above here. Okay, so it looks a little something, maybe like this. Here's 0, and here's 1 over here. If you actually wanted the integral from -1 to 0, it'd be negative because the region is below. When you get that y value, that f of x, remember that height, it would actually be negative. The base is always going to be positive, the difference of the x values. Stuff we'll speak about next year. Don't worry about it for now. The idea is I know everybody's able to come up with that, picture right there. And to get the area, well, if you want the area between a function and the x-axis, what do you do with that function? Very good. Integrate that function, all right? So the integral of x over 2x squared plus 1, quantity squared with respect to x. Don't forget those bounds, okay? Here I'm going to integrate it from x equals 0 up to x equals 2. And you got to be able to set that up. And the nice thing is, on the AP exam, if it's the calculator question section and you set up a definite integral, you're allowed to go right to the answer using the graphing calculator. Now, make sure you look on the quest that I hand out for this, okay, that you guys got to do. If it says show work, show the integration process, you can't go right to the answer. Usually we do that for stuff that's really difficult to integrate. This is not difficult to integrate, but how would you integrate something like that? Very good. I'd use U substitution as well. We don't know how to deal with U substitution with the definite integral. Things are going to change around, believe it or not. We'll speak about that mañana. So for now, we'll use the calculator on this, but this is one that could is very doable by hand. Let's set up a little math, 9. Integral from 0 to 2. And instead of writing this whole thing out again, I have it sitting here in y1. How do you get to y1 on the graphing calculator? Well, alpha y1. All right, we'll integrate this thing with respect to x, hit enter. Okay, and I get 0.2 repeating. You could try to frac it up if you want. See here, it doesn't frac it up, but it's really just 0.2 repeating. So if I do this, maybe it'll frac it up. It does, it's 2/9, which I already should have known anyway, but regardless, yeah. Okay, so anyway, so there I'm going to get 2/9. Okay, you could even say 0.222 if you want to. Why do I feel like something's wrong? Something is wrong. What did I do wrong here? Okay, take a look. What did I do wrong? Tell me. Oh, I did the integral from 0 to 2, when I should really be doing the integral from 0 to 1, okay? So just be careful with that. I don't know why that happened, okay? Would we do that in the last problem? So I guess that's probably what happened right there. Don't chalk that up to mistrust, students. All right, so we do the integral from 0 to 1. It's kind of cool, though, because then we get to play around with this. If you hit second enter a few times, you'll get back that expression. Okay, you could change it to 1 right there. Don't rewrite the entire thing. Hit enter, and I'm getting 0.167 if you want to write it that way, or it does frac up to 1/6. Okay, so we'll stick with 1/6, but you could also say if you want 0.167 or 0.166 if you're a lousy, stinking truncator. Execute order 0.166. See, that's, a truncator or SIF. Anyway, so remember, if you want the area between a function and the x-axis, as long as the region is above the x-axis, you want to integrate that function. Make sure you put your lower bound on the bottom, okay, your upper bound on the top. And usually when you set up your own integral, the lower bound will be lesser in value than the upper bound because you're going to integrate to the right. You're going to integrate forward. You could put a 1 right here and a 0 right here. You'll actually get a negative 1/6, something we'll speak about. But if you set up your own integral, try to integrate forward. Remember, if you want to evaluate a definite integral, you integrate the integrand, plug in, can you see what I'm just pointing at? You integrate the integrand, okay, plug in the upper bound, subtract the plug in of the lower bound. Sometimes the calculation can get a little annoying, okay, so it's really important to practice stuff like this without the calculator. Then you have the calculator to actually check. I should try that homework tonight. Hopefully it's not too terrible. 2 problems without the calculator, 2 problems with the calculator, I believe. And we'll speak more mañana. Hope everybody's healthy and safe, and take it easy, y'all.